Hey everybody, welcome to another CS302 assignment. And for this assignment, this is going to be involving graph theory. And we're going to essentially, for the theme, we're going to have this celebrated game in the Resident Evil franchise, Resident Evil 4. And in this game, you play as Leon Kennedy, and his objective is to save the president's daughter, Ashley. And we're going to be in this town in Spain, I believe. And essentially in this town, there are several locations. And let me just show you here in the PDF. This is going to be all the locations we have in this town. And each location can be connected to each other by some edge. So if you think about it, each of these locations will be a name of a node in our graph. And we're going to have several different possibilities. We're going to have different edges we'll have. And essentially an edge will connect from one location to another location. And the idea is you want to find a path where we always begin so Resident Evil 4, we begin at the village. And you want to find a path to the church. That's where Ashley is hiding when we first discover Ashley in Resident Evil 4. And these locations will be our nodes, and then we're going to have a set of edges that connects between each node. So, and then of course, we'll have some type of a DFS modification to find a path from the village to the church. That's the idea. Now, the only update here is that since our nodes are labeled by strings, we're not going to use a vector, we're going to use an unordered map to maintain our nodes. But luckily, you can use the unordered map from the STL libraries. Don't worry about using your own custom unordered map. So it's going to make life a lot easier. And in fact, even for your adjacency list, since each node is not labeled by integer, labeled by string, then we have to use unordered map. So we're going to have an unordered map of linked lists to maintain this adjacency list. But in reality, the only difference will be is you have to use a string as the index. But remember, with maps, it's very easy to do that. But I will, of course, will go over a little bit of that with you just to get you started. And then also, what we're going to have is in this version of our simulation, each location will have a set of zombies. And you have to essentially shoot the zombies with Leon. Now, Resident Evil 4 was not really a survival horror. It was more survival action. It was horror action type of game. But we're going to kind of simulate this survival type of aspect where, remember, in Resident Evil 2 or the classic Resident Evil games, you try to daze a zombie and run past them quickly. So use up one bullet to daze a zombie and run past them. So if there's, let's say, 3 zombies at a location, you need 3 bullets to daze each zombie and then run past them. That's how this is going to be played. So you will have to store the amount of ammunition Leon has. And of course, we want to we're going to have to maintain how many zombies we have at a location. And we're going to have sort of a visited array, but it won't be visited. It's going to really store how much ammunition we had when we arrived at a node. And I will, of course, will simulate this for you to kind of see how this is going to be used as our visited array. So it's going to be a slightly modified version of DFS. So let me go ahead and just kind of show you the input files. I have the data structures given to you here in the PDF, but I'll go ahead and go over these data structures more visually here on OneNote with our given input files. Okay, so here is one of the input files. So I called it map01.txt. And it basically this file contains all your edges, basically. So if we look at this, we have village space castle, which means there's edge from village to castle. So you have these 2 nodes and they're connected along this edge. And of course, in this direction only, because it's going to be a directed graph. Then we have village Grand Hall. Then we have village lake. And also in this file, we have also castle goes to Grand Hall, castle goes to mine, Grand Hall goes to mines. And of course, there are more edges. I'm just going to focus on a few for right now, just to sort of not overcomplicate the example, but we can visualize this. So these names here in red, that's going to be the node IDs. And since our node IDs are not integers, we have to use maps accordingly. And these numbers right there represent the enemies at the location, which again, we have to store these numbers into a separate map. So here's how we can visualize this graph in our program. So here I provide for you, here's the data type you want to declare. So of course you can include unordered map, you can include list as well in your program. So this way we have a map that maps a string to a linked list of strings. That's going to be a adjacency list. So for this graph right here, we can visualize it like this. So here's the adjacency list. And if you think about it, an unordered map can be thought of as just an array where we use strings as the indices. So for this list, adjacency list at index village, it returns this linked list, and each linked list contains a string, and it contains the neighbors of the village. So Castle, Grand Hall, Lake, and again, this could be in any order. As you can see, those are the 3 neighbors we have right there. And then in this example, we don't have any neighbors for Lake or Mines, which is actually, I believe in the maps file, there are neighbors, but we're just going to focus on this subversion of the graph. Grand Hall has 1 neighbor, Mines, and then Castle has 2 neighbors. So very simple to construct this data structure. And here's kind of how you would do it. So in this PDF file, you can read in. So you have your input file stream variable set up to read from this file. You have your from and to. So for example, from could be village and to could be castle. In this line of code right there, that's going to insert this neighbor into village's neighbors list. So you go into the list at index from. This is going to return back to you a linked list object. You call its pushback function and you insert castle into this node. And then for the other neighbor, you read in village space Grand Hall. So village is from, Grand Hall is to. And you basically just, same idea, go to index village, it returns a linked list object, and you insert a new node to the back of that linked list and pass in that to neighbor, which will insert a new node with the Grand Hall. And then of course, do it for every single node or every single line in the input file. So because we can use STL, this process is actually very simple. So you of course have to construct this structure so that way you can actually write your DFS code to traverse through your graph. And of course, the visualization is right there for you, but you're going to be mostly working through this. Now, you also want to store enemies at the locations. So going into this input file, there's another file you're also given, and it's called enemies. And this tells you for each room how many enemies you have. So you want to create another map right here. You're going to map a string to an int. So string is going to be the room name, int will be the enemies at the location. So you want to have a separate map that maintains this. So you want to essentially know how many elements or how many enemies you have in a location. And of course, your predecessor map, it won't be an array in this case because we're using strings. It's going to be a map that maps a string to a string. So it maps a room to its predecessor. So for example, if you're traversing through your graph, let's say right here, you're on village and you're going to go to castle. Well, then castle's predecessor in this path is village. So you go to this predecessor map at index castle and assign village to it. So in reality, it's the same exact idea, except they're using maps, but you can treat each string as an index, if you will. So it's literally the same exact concept, just maps will allow you to implement this with strings versus just integers, what vectors do. Okay, so that's how you would essentially build these structures. Now, this under a map right here, string to int, and location, this is going to kind of be your visited array, because you might revisit a node multiple times if a better path is found. So what I mean by this is that, for example, like right here. So when you start this simulation, Leon will always have 10 ammo at the beginning. So at the village, will assume, at least in this case, for this input file, village has no enemies. So nothing is going to be used in this case. Now, suppose we go to castle next. We arrive here, okay, there are 7 enemies at this location. So we have to decrement our ammo down by 7. So that means we are left with 3 ammunition at this location. Now, from castle, we can go to Grand Hall, or we can go to mines, because we have 2 neighbors. Suppose we choose Grand Hall. Okay, so we'll go to this location, and we have 3 bullets for Leon. We have to use up 2 when we arrive at Grand Hall. So now we're going to be left with just 1 ammunition. Then from Grand Hall, we go to mines, and then now we're left with 0, essentially. So this number in green is going to be sort of a parameter, but we also want to store this in this map, because you want to know how much ammo we used up last time we were in this room. So think of each room we go to, we immediately save our progress at a typewriter, let's say. So what happens now, for mines, you have no more ammo left, so we can't really progress our traversal. So we have to return back to the previous node, back to Grand Hall. Then from Grand Hall, there's nowhere else to go. We go back to Castle. Now with Castle, we have 3 ammo, so we could go to mines. And then what happens is we're going to overwrite this. So now we actually have 2 ammo when we arrive at mines. So even though we've already seen mines before, so remember, we already traversed here, so a regular DFS will not try to re-explore mines. But because this path led us to have more ammo at mines, it's actually worth to revisit this, because now with a better scenario, maybe now we can progress easier. Now suppose, let's say with only 2 bullets, we can't really progress too much. Well then, we have to back up, back to Castle, and in Castle, we already tried Grand Hall, so we're going to back up to the village. So we backed up to village. The village, we already tried Castle. Our other neighbor would be Grand Hall. And notice that right now, when we return back, we reset our ammunition, because we're almost like we load previous save points, and using our original ammunition amount 10, we then try a different path. So here we can go to Grand Hall. We've already seen Grand Hall, but however, in this scenario, we have 10 ammunition. Grand Hall uses up only 2, so we actually have more ammunition in Grand Hall using this scenario. Now, from Grand Hall, we can go to mines. We've already seen mines before, but last time we were at mines, we had 2 ammunition. Well, if you go to mines in this scenario with 8 bullets, we actually now we're going to have 7 ammunition at mines. So a better path was formed. So what will happen is we have to constantly reassign the predecessor array if new paths are found. So this is almost like doing Dijkstra's, but we're going to be using DFS instead, but Dijkstra's would be the actual better algorithm in this case. But you want to actually practice our DFS because it requires less data structures than Dijkstra's. But the idea is that as we traverse our graph in DFS fashion, we might re-explore nodes again if we find a better scenario. And we saw here, we did go to mines earlier, but earlier we had actually less ammunition. So essentially, if you're traversing your graph, let's say you're at a certain node, and you want to go to mines, you check in this map, ammo at location. If last time we were here, we had 2 bullets, and right now, with 8, minus 1, we'd have 7, then it's actually worth to re-explore. We're going to rewrite in this map for mines. We're going to overwrite it with 2 with the value 7, and then we're going to resume. So whenever we arrive at a node, we're going to store the amount of ammunition we have left over once we arrive at the node, and then we progress our traversal. So this is going to be kind of like, this is going to be our visited array, but however, instead of being a Boolean, we store an integer in this spot, and we constantly override it if more ammunition is found, because earlier this path led to fewer ammunition, then this path was actually better, but it turns out this path was actually even more effective. So then Grand Hall, Castle, and Mines did have to actually, they updated their predecessor arrays, because right here we had Castle predecessor was Village, then Grand Hall was Castle, but then later on when we found other paths, Grand Hall's predecessor updates to Village and Mines updates to Grand Hall. So that's really sort of the idea for how we're doing this. So we're doing just DFS, but we're going to use this ammo at location as our visited array, and we might re-explore nodes if we have more ammo at the location. And then if we do, we have to update the predecessors as we are finding multiple paths. Okay, so let me just go ahead and show you DFS code slightly and give you an idea of how to code this up. So also another update is if you want to traverse to your neighbors list, here's the 2 ways you can do it, but I kind of went over this in class as well, but just in case this was missed, here are the 2 ways you can traverse through the neighbors list for a given node. Okay, so here's the function you want to write. So save Ashley is going to be our DFS function. We pass in the string Leon. So this is actually telling where Leon is. So in our DFS we did in class, current told us which node we were currently standing on. Here we have a string Leon, which tells us where Leon is. So initially we're going to pass in village. So that's going to be where Leon's location is. Then its integer ammo will tell us how much ammo Leon currently has right now. Then we have our adjacency list right there, which I called it map, but you can, of course, can rename these as you like. Then we have this map that will store the enemies at the location. So remember, we want to just note how many enemies we have at each location. So we pass in this map. Then this is going to be our visited map, ammo at location. So it's going to tell us how much ammo we had at a location last time we were there. And then we have a predecessor map right there. So it's going to be just a modified version of DFS, but we return a Boolean instead. So same idea, we check. So if we're at this node, so we have our enemies at location instead of visited for Leon, if this number is less than this ammo passed in, then there's no point. We may as well return false. Let's get out of here. There's no point to actually traverse this location. Once we pass this point, right here, we're going to simply write. So we take our enemies at location, ammo at location at index Leon, and we're going to reassign it with, well, the ammo we have minus the enemies at location for where Leon currently is standing. We're going to overwrite that right there. There's no point of C out really, so we can skip that. And then we have this for loop right there. So we basically look at every neighbor for where Leon currently is standing. And then, of course, we can have if statement wrapping around, or we don't need to because we do kind of check for it here in the DFS, but you also can check right here. So if enemies at location, ammo location for the neighbor node is less than our current ammo amount, then there's no point to go to this. But this is also optional because since we do check for this at the top anyway, we could also omit this here. We're going to set the predecessor, and we call the function save Ashley. We pass our neighbor ID and the rest of our content. Now, in this the difference with this function we have here for save Ashley, it returns a Boolean, true or false. If it returns false, that means we were not able to find a path to Ashley, which means we have to go back and pick our new neighbor and then try something else. If it returns true, however, that means we found a path. So we can return true immediately all the way back to the beginning. And then from the beginning back in main, we can then use our predecessor array to actually output the path that led us from the village to the church. So really, you gotta take this DFS function and modify it. So a little modification, but the other main difference is this save Ashley DFS function returns a Boolean, true or false. So you want to essentially determine if it returns false, that means try a different neighbor. If it turns true, then return, and you're going to relay true all the way back to the beginning. And of course, back to the beginning, meaning back in main. And then for main, you can, of course, using a predecessor array, you can output the path that leads from Leon to finding Ashley. So let me go ahead now and just do a sample execution of this program. And then, of course, that'll be the conclusion of the video. Okay, so the PDF contains the sample input and output. I also will provide you with other inputs and outputs, all the input outputs that will be used in CodeGrade. And so I'll provide that for you. Let me go ahead and just show you how you're going to do this. So you have only one file, just an int main. Don't worry about writing any classes because you can use all the STL. So it's going to be much easier to write this. So you just simply compile this, G++ main.cpp. There we are to run this. Let's run it. So it's going to, of course, scream Leon because Ashley needs help. So I'm going to pass in for the file. Let me just make sure I have the right file names. So it's going to be map01.txt. And it's, of course, going to read that file. It reads this file in, and it's going to create this adjacency list for us. Enemies file is going to tell us how many enemies there are at each location. I'll pass in enemies 01.txt. And then we output I'm coming Ashley because we found a path, and here's a path that locates from Leon to Ashley. That's it. So I have several input output files I'm going to work with. So I believe how I have it set up that there's actually every path leads to a success. And the reason why is because, well, it kind of breaks my heart in Resident Evil 4 Remake when Ashley does get captured. It's just like the worst feeling ever. So we want to make sure we don't have any case where Leon fails. Now, in theory, you could have it where back in main, if it returns a false, we output some negative message, but I'll have it set up where there's always going to be a path for Leon that will successfully find Ashley. So I will provide you the other input output files in CodeGrade and on in Canvas announcement. And that's sort of, I guess, the end of the video. So hopefully this gave you some help, or at least gives you some idea of how to get started. So I guess happy coding, and till next time.